So I'm going to go over common mistakes on the midterm today before we go back to root locus and PI controller design. If you have any questions about how I graded things, markdowns, or if you think I made a mistake, please let me know, and I'll gladly take a look at it. The TAs did not. Oh, there's an Apple Pencil here. So the TAs did not. I'm gonna leave this here. The TAs did not grade this. I graded it, so I was the final one that sentenced your fates. So if you're unhappy with it, come talk to me. Do not villainize the TAs. And uh, yeah, so we'll go over that, and hopefully you'll come away with a better understanding of some tricks and ways of solving the exam. The exam, I'm going to bring the exams every day this week until Thursday, and then I'll bring the exams back for midterm two. So if you don't grab the exams by then, just come to office hours. I'll probably bring them to office hours as well. And yeah, just let me know if you want to grab them. If you can't grab them this week, no worries. For online folks, I will email your exams today. I'm just getting around to it. It's been a busy week. All right. So I'm going to go over quickly common mistakes for each problem. Overall, number one is a tricky one in the sense that I define the state variables as x dot and x dot plus x. And this really tripped up a lot of people. Here's a very common mistake. So basically how I defined it is that we want to say that x1 is equal to x dot, and then x2 is going to be equal to x dot plus x. Traditionally in the past, I say x1 is equal to I don't know, like x, and x2 is equal to x1 dot, which is equal to x dot. So I was trying to steer you away from that kind of thinking, but I don't think I did a sufficient enough job of doing that. I did say in the review that this is possible, that we can have unique ways of defining state variables. You might have noticed this in MATLAB. Even the way MATLAB defines state variables is very different from how I define it. That's why in one of the homeworks, when you were doing initial conditions, you saw this huge value when you did initial condition responses, because I defined and gave you state conditions or initial conditions based off of my definition of initial conditions and not based off of MATLAB's definitions of initial conditions. Anyway, so the way I define x dot, and I gave you the differential equation here. The first thing I would do is I would try to rewrite this differential equation as x1 and x2, which is going to be, this is going to be equal to, this is going to be equal to -2. So I'm going to pull the 2 out. I'm going to pull the -2. I get x dot plus x plus f of t. And from there, you can just see that this is just equal to -2 times x2. And that's my first row. So I guess this another way of saying this is x1 and this is x2. And when I do the second row, where it's x double dot plus x dot, what I'm going to do is I'm just going to take this differential equation and just add x dot to it. So then I get -2 x dot plus x dot plus f of t. And that's just equal to -2 x2 plus x1 plus f of t. So using that, I'm able to then just fill in this second row here. You get x1 with 1, -2 for x2, and then 1 for f of t. So that's the first problem. Generally, for this one, it's misleading, but once you are able to write it like this, it becomes a lot simpler to solve. And the thing about parts B and C is that even if you gave me the wrong part A, I worked with it. So if you solve part B using your A matrix, I I gave you full credit if you got B right. And then if you answered the stability question part C using your A matrix correctly, I gave you full credit for that as well. So I manually checked everyone's polls. So I worked with whatever answer you had in the previous part with parts B and C. So I still gave you credit for B and C. I tried to decouple that. So that's how you do part A. One note about part B, not as many people made this mistake, is you want to include your pole zero cancellation for part C. So if you have pole zero cancellation, you still want to include those poles and zeros that were canceled out. Problem 2 was more or less good. Most people stuck with the signals method. With the signals method, you only need to define one signal point after the summing junction. You don't need to define this point because y is defined as that summing junction. So we just say that y is equal to d plus g1 multiplied by g3 times x1. Oh, yeah, I have it down here. And then x1 is going to be equal to g2y times or minus g3. So there's a few people who left out this x1 here. It's okay to have x1 within its own equation because all you have to do is you just rearrange the equation to this form here and do some substitution and you get the final answer. So problem 2 more or less straightforward. It's just a few people forgot to include this x1 here. Don't forget that. You can't just have a block by itself. It's going to be always a block multiplied by a signal. And you can't add a signal into a block. So you can't do like D plus G1. That doesn't work. D is a signal, while G1's a block. These are incompatible. You can't add blocks. This is incompatible. Now, there were a few brave souls who decided to do the block diagram reduction. So if you were to do the block diagram reduction, another way of redrawing this block is like this. It's just a feedback with a block G1 and G2 being in series. And then once you get that, you then just apply the series rule. And then you can see that this series is actually the H block in the negative feedback system. Then you apply negative feedback. So redrawing your block diagrams should also help make block diagrams a little bit more intuitive. It's not like I created this block to trick you. This block is actually from a design I work with in the lab for disturbance observers. The actual block itself is a lot more complicated where it has like this whole component here plus other components here and whatnot. And so I'm not trying to trick you, but this is just something I had to deal with as well. And I reduced that block using the signals method personally, but I tried solving it using the block reduction method as well. And what I do is I just redraw it, which helps a lot visually to see if something's in feedback, something's in series, if something is the sensor or something's the plant. All right. Finally, for number 3, the big trick with number 3 is, so this one was also a little bit tricky, one layer of deception. But the big trick that I give you here is that I give you the factorized form of the second order transfer function. In the review the day before, I gave you the definition of the DC gain of the system, which is just going to be limit as s goes to 0 of g of s is the DC gain. So I really appreciate those who showed up to the review session and applied this definition immediately. That was just a easy 10 points. By the way, the breakdown of the points of how I graded each part is on Canvas. I put up a rubric for a breakdown of each points. So you can see the breakdown, but I guess I'll write it down here. So this was worth 10 points. This was worth 5, and then 20. Oh, I wrote it. It's in the solution. So I have it in the solutions sheet, how many points is each part worth. So I did update the solutions to have that. So if you do have the old version of the solutions, this is new now. So you apply that, you just basically plug in S is equal to 0 and you get the DC gain. And in the review, I talk about why this is the definition of the DC gain. What does K need for the system to be critically damped? So while it can work, you can write this transfer function into this form here, K times omega n squared times s squared plus 2 zeta omega n s plus omega n squared, and you set zeta equal to 1. A lot of people did that. But, the definition of a critically damped system is two real repeated poles. And I give you the first pole, which is -1. So you just have to set k equal to -1 again, and you get two real repeated poles. You don't have to go through this step here. This is unnecessary. This is extra work. All we want to do is apply the definition, two real repeated poles. So we have a pole at -1. So then k has to be equal to 1 for a pole to exist at -1. So you don't need to even show any work. If you just write -1, I know that you understood the question. So then when I ask you for a critically damped system, or sorry, that was critically damped. If I ask you for overdamped system, the definition of overdamped means that there's two real unique poles, meaning that you cannot have repeated poles and it needs to be real. And the only condition for that to work is when k is not equal to 1. And I already gave you the definition that k is greater than 0, so you don't have to include this part. If you included k not equal to 1, I was okay with that. Or if you said k is less than 1 and k is greater than 1, I'm also okay with that. But the point is that just by looking at this, you don't need to solve for this and say, well, zeta can be any real number and try to solve for it. It's just really, really hard. There were a few people who were able to get the conditions down to k. I think it was 1 minus k squared is greater than 1. And then from there, they're like saying, or I think it was k minus 1. I think it was k minus 1. From there, they said, well, k has to be greater than 1. Well, or greater than 0. Well, so this is true. K needs to be greater than 0. But since we're taking the square of it, k can also be less than 1. And it's also true because we're taking the square. It's always going to be greater than 0. The only time this condition is not true is when k is equal to 1. Then we're saying 0 is greater than 0. That's not true. So from this, you can just say that k is not equal to 0. Those are equivalent conditions. Finally, this one's, I did this with my first exam ever when I taught this class. So there's two ways of solving this. And this is where I tell you to kind of think about the strategy before you jump into it. I'm asking you to find dy dt. So basically what I'm asking you to do is you want to take the inverse Laplace transform of s times y of s, which gets you dy dt. And the reason why you do that is because s times y of s is going to be equal to s times g of s times u of s. So I tell you, it's like a little bit tricky because I give you a ramp input. And then, so then you have to deal with a partial fraction expansion of a 1 over s squared term. But if you apply this s times y of s here, you can actually cancel out one of the s's there. And instead you get this form here, which is, you just need to take the partial fraction expansion of this instead. So you only need to find the partial fraction expansion of 3 terms. It's a lot easier. You don't have to find the 4th term. In case that I did add a new section the day before I printed these exams out, I did give you this, so I think it wasn't exactly fair because I didn't point it out, that this is how you take the partial fraction expansion of repeated poles. So let's say you didn't do this trick, right? And instead you want to work out the long way. Well, if you still think about this here, you're like, okay, well, this here's going to give me y of s, where if I take the inverse Laplace transform of y of s, I get y of t, and I need to take the derivative of y of t. Then I get y of t, and then I need to get the y dot of t. Well, if you look here, when you take the inverse Laplace transform of k1, you get a constant, and you take the derivative of that constant, it goes to 0. So you don't even need to solve value of k1. K1's not needed. You only need to find the partial fraction expansions of k2 through 4. Once you do that, you get this term here. We get k1, and we don't need it because when we take the inverse Laplace transform, we get k1, but that's not the final answer. We take the derivative of it, then we get this. So it's kind of one of those things where it's kind of, I want you to think ahead a little bit before you solve the problem on like, where can I save steps? What information do I not need and I can get rid of, and to make my whole process of solving it easier. In general, for this problem, I gave you credit. If you just set up the partial fraction expansion, I gave you credit there. If you got one of the constants wrong, I took 2 points off. If you got another one wrong, like let's say you got 2 constants off, I just took an extra point off instead. So this one's very algebra heavy, so I don't really emphasize too much on the algebra, but hopefully, yeah, this is as hard as it'll get on the exam for partial fraction expansion. Are there any questions? I will admit, I think this year exams did have the most level of trickery, so don't feel bad if you got bamboozled. Midterm 2 should be a little bit more straightforward, and the scope on midterm 2 is a lot more focused. People tend to have a harder time on midterm 1 anyway, because, you know, if you are working for years or you come back to grad school and you haven't taken an exam in God knows how many years, it's kind of rough time management wise and working under a certain time constraint. In reality, in projects, we always have more than 50 minutes to do something. So don't feel too bad if you didn't do too well. It's usually hard for people for their first exam. My first midterm I took in this class, I got 50%, and look where I'm at now. I'm teaching you guys. So and I actually had 2 midterms in that class. It was the second midterm where my instructor, I called it the revenge midterm, where he decided that the average was too high and wanted to punish us all. It wasn't because the average was too high, but it was because someone got caught cheating, so he decided to give a revenge midterm. So we all got punished for it. Fun times. Anyway, the second midterm, like I said, if you're keeping up with root locus, you understand the fundamentals of root locus, there's a lot less space for me to be deceiving. It's a lot more straightforward. But please keep on top of homework. If you have questions, reach out to me or the TAs. Even if you can't make it to office hours, just email me. I'll try to get back within 24 hours. If I don't reply within 24 hours, just send a follow-up email. Don't feel bad about bothering me. Sometimes I just get buried in my emails and I just, you know, I look at it and then I think I'm going to reply to it later and I end up not replying later. If that happens, email me again. All right, so today we're going to be continuing PI controller design. PI controllers are easy to design because all we're doing is we're adding a pole. And let me just recap yesterday. All we're doing is we're adding a pole and a zero very close to each other. So by doing that, we actually more or less keep the overall shape of the root locus, because think of this pole and zero added. So the pole has to be at the origin, but the zero just needs to be close to the pole. Think of that combination as like a self-contained root locus, like a self-contained branch. So while it does influence this branch a little bit in my drawn figure here, it won't affect the shape too much. And the purpose of it is to just reduce the steady state error. We don't really care what it does to the transient response time because we got the PD controller to do that. So in the example here, I just basically showed you the steady state error, and then by adding the PI controller, we're able to remove that steady state error. And I showed you the MATLAB code for that today. So that's PI controller. It's my favorite part of PID controller design. And when we talked about PID controller later in this section, we're going to be talking about the order in which we designed this. One last thing about compensator application. So if we were to see this in a hardware application using an analog circuitry, we have an op amp here again, and instead the PD, the capacitor and resistance are flipped here, but here the resistor and capacitance is flipped instead for PI application. And basically the way it works is current is pumped into the capacitor based on the input voltage and resistor values. The current over the capacitor causes the capacitor voltage to change over time. So as the capacitor fills up, the voltage changes. Hopefully you remember that from your very simple EE class. The last time I took an EE class was in 2014. So I actually do not remember that. But anyway, you can take that for granted. Then changing the voltage becomes the output. So the changing voltage becomes the output signal. And the change in voltage is calculated as, so the change in voltage or delta V out is equal to 1 over our RC times the integral of V in taken from 0 to our evaluated time. So that's the integrated portion is right there. We just take the integral of the voltage taken in over time, and that'll give you our change in voltage as the output. Um, so now we can talk about lag compensators. So lag compensators are actually very similar in structure as lead compensator design here. So I actually have this corrected in the notes. I do have it saying lag compensator. So lag compensator is a passive network that adds a compensator pole near the origin and a zero near the pole to reduce steady state error. So we want to have a pole at the origin. We need active circuitry for that to happen. But in passive systems, the pole that we add cannot be at the origin. It can only be close to the origin. And we want this relationship. So lead, these are flipped, but in lag, we want the zero to be to the left of the pole, and the pole is going to be close to the origin. And this looks very similar to the lead compensator design because we're adding a zero and a pole, but the location of the zero relative to the pole and the location of the pole is what separates the difference between a lag and lead compensator. Are we good here so far? Okay, so the reason why we say the zero needs to be near the pole, it's the same as the PI controller design, where when we have the zero close to the pole like this, and we have the origin right here, then the root locus will largely remain unaffected because this branch here is contained. We don't want this, we want these to be the closest to each other, basically. So we keep it contained, and the pole cannot be at the origin. So we need some distance from the origin. Okay, so lag compensators emulate PI controllers with a pole near the origin. It's not a pole at the origin, so that's why we say it emulates it. It's kind of like it, but it's not really. It's a passive network since added pole is not the origin. It does not increase your system type. So we cannot make steady state error go to zero. We can only make it smaller. So systems with steady state error, infinity steady state error will remain at infinity. So we can't apply this to a system that has infinite steady state error. It's not designed for improving transient response time. If anything, it'll make it worse. Same with the PI controller. It also will not alter the root locus shape significantly. So let's look at this. I feel like this is very redundant. All right, so effect does not increase your system type and maintains general root locus shape. It reduces finite steady state error. That's what its purpose is for. It's a passive network, and it's a lot cheaper than an active network, but electronics today are so cheap, I find it very irrelevant. Does not reduce steady state error to zero. That's the downside. It may increase transient time, like settling time, longer periods of oscillation. It's not may, it will. But I guess I don't like absolute statements because it might not. So steps for compensator design, lag compensator design is similar to PI controller design. You just place a lag compensator pole near the origin, and then you pick up compensator zero such that the zero is close to the pole and to the left of it. Just a note about this is that, and this is true with PI compensator design, that the further the zero is away from the pole, the more the root locus shape will change, which we want to avoid for PID and lag lead compensator design. One thing about your pole and zero placement is that depending on how close your pole and zero are to each other, it's going to change your steady state error value. And I'm going to talk about that in the next slide. So the reduction of steady state error is proportional to the ratio of your zero divided by your pole of your added pole and zero. So let's define a general uncompensated system that's factorized like this. And now I'm going to call the DC gain. So we're going to apply the DC gain because at steady state error, we get the DC gain of a system is when we take the system to steady state. So at steady state, the DC gain is going to be this. Let me call it KU. So DC gain, yeah.
What was that statement you just said?
Oh, yeah. So the DC gain of a system. Oh, let me. The DC gain of the system is basically finding the steady state value of G of your plant. Yeah. So maybe I'll write it down. DC gain is finding the steady state value of G of S. So let me call that KU for K uncompensated. And we're gonna apply the final value theorem because the final value theorem is basically finding the steady state value of G. And we just let S equal to 0. And all we get is this. We get Z1 times Z2 times all the zeros. And then you get P1 times P2 times all the poles all the way to Pn. All right. So this is Ku. And then for the compensated system, because now what we have is I'm gonna call it Kc. It's going to be limit as S goes to 0 of our compensated system, which is our controller C of S multiplied by G of S. And that's going to be equal to, and it's going to be equal to limit as S goes to 0 of K times S plus ZC divided by S plus PC multiplied by G of S. I'm not gonna write it out. And then I basically apply S is equal to 0 and I get K times ZC over PC multiplied by Z1 times Z2 all the way to ZM, then P1 times P2 all the way to Pn. And this is equal to K times ZC over PC times KU. So KC is equal to ZC over PC divided by K times KU. And I wouldn't worry too much about this K here because this K is just dependent on where our pole is going to be at, where we want our closed loop poles to be at. So let's just assume that it's just a constant, right? Let's just assume it's K is equal to 1 just for this analysis. It's very irrelevant. Basically, what's important is that your ratio of your yeah, so what you want to do is that your ratio of your 0 to your pole is what determines the value of your steady state error. And actually, I think the textbook doesn't do a great job at this, but I actually am going to rewrite this a little bit. So I'm going to put that K into the G here and take the K out instead. So the reason why I did that is because we choose this K here. We choose this based on our root locus. Like we're based on our closed loop pole location, our desired closed loop pole location. And then we just keep that value. It just stays there. So we don't actually change it. So then this would be a better definition. So let's take that out. All right. All right. So once we have that, we can see that our KC is dependent on the ratio of ZC over PC multiplied by KU. And we want, basically for effective error reduction, for ESS reduction, we want KC to be greater than KU, which implies that ZC is greater than PC. So this is actually a works both ways statement. Okay, so the reason why I'm talking about this, and now we're going to have a flashback to chapter 7. From chapter 7, the steady state error of a step input is defined as this: ESS of a unit step input. So a unit step ESS is equal to 1 over 1 plus KP. A unit ramp has a steady state error of 1 over KV, and a unit parabolic has steady state error of 1 over KA, where we can find our constant values defined as such. Let's see. KP is equal to limit as S goes to 0 of G of S, which is the same as our KU. KV is equal to limit as S goes to 0 of S times G of S, and KA is equal to the limit as S goes to 0 of S squared times G of S. And these are for the uncompensated systems. So then if I want to find the error of the compensated systems, it's just going to be I guess KPC is going to be equal to KU times KP. KV, I need to be very careful here. Compensated is going to be equal to, and you know what? What I'm going to do is I'm going to write it out. It's going to be equal to it's going to be equal to K. Oops, sorry. Should be KC here. Be KC. I do not want to write that out, actually. We'll leave it. It's going to be equal to limit as S goes to 0 of. No, sorry. S goes to 0 of S, C of S, G of S. And KA compensated is equal to limit as S goes to 0 of S squared times C of S times G of S. So I need to be careful there. So KPC compensated is just equal to KC. But KV and KA, you need to apply the S and the S squared terms as well. So what I'll do is I'll do an example. So hopefully it makes more sense on how we pick our steady state error, or how we pick our zero location and pole location based off of how much steady state error we want to reduce. Any questions? Okay, so we're going to design a lag compensator to reduce the steady state error by 10 times and damping ratio with a damping ratio of 0.5. So we're given this simple second order system. And note that I don't tell you the steady state error for what input. You have to figure that out yourself. But we can see that this is a type 1 system, type 0 system, meaning that we have steady state error for a unit step input. So we're going to be finding our Ka value. So type 0 system implies that we have constant steady state error for a step input. Because there's no poles at the origin. Do I have a second page? Oh, I do. All right. Now, usually I'll say we could just go on MATLAB and determine the gain and um, determine the gain for the corresponding system to have 0.5 damping ratio and figure out the steady state error based off of that. But actually, for this kind of problem, when there's only two poles and no zeros, it's actually really easy to do it by hand. And I'll just show you by hand how we can do it. Okay, it's easy for me. Maybe it's not obvious yet. But with practice, promise you, you will see it better. Okay, so let's just draw this out. We have a pull at -1 and a pull at -3. And just by looking at this, because we only have two poles, our asymptote angles is going to be 90 and -90 degrees. And our asymptote location is basically just the average location of the poles and zeros combined, divided by the number of poles minus the number of zeros. And since we only have two poles, then we just add up the location of the poles, which is -3 plus -1, which is -4, and divided by the number of poles, which is -2. So our asymptote is actually at -2, and the root locus does, because there's only poles. This is what our root locus looks like. It'll actually look exactly like this on MATLAB. So just from knowing that, we know that this point here is -2, which is equal to the damping ratio multiplied by the natural frequency. And maybe I'll draw this out better. So I'm going to say this is -2, and then I'm going to give a distance measure right here. This point here is your negative zeta times omega n. All right, so one thing about zeta is that the constant lines here is going to be zeta, for it to be constant, is going to be these little lines going from the origin. So 0.5 is going to be somewhere there. I don't know if it's actually there, but basically we're finding this intersection point. And to do that, we also need the height information, where the height is going to be omega n times 1 minus zeta squared. And since we already have zeta squared, or we already know the value of zeta, and we know the value of, or we know the location of this root locus, basically the closed loop pole on this line here, I'll highlight it. It's going to be at -2 plus or minus omega n times square root of 1 minus zeta squared times j. Because we know the real part is at -2. It doesn't deviate away from this point. So then we say -2 is equal to minus zeta omega n, and we know that zeta is given to be 0.5. So minus 0.5 omega n, then we find that omega n is equal to 4 radians per second. All right, so then from there, when we plug these values in, our closed loop pole is going to be at -2 plus or minus 3.46J. So that's we can do that graphically. Let me give you a alternative method as well. Any questions so far? Okay, so alternative method is that we have this open loop transfer function G, and basically it's a second order system, so our closed loop transfer function is going to be a second order system as well. So T of S, and when we do the root locus, we basically multiply it by K here. And we're changing the values of K to plot out the root locus plot. 1 over 1 plus KG. That's our closed loop transfer function. All right, so when I work this out, I actually get this equation here. And this is the trick that you should do if you like numbers instead of drawing stuff out. You get K divided by S squared plus 4S plus 3 plus K. And then you set that equal to your second order. I'll call this K1. You set this equal to your generalized second order your second order generalized second order transfer function that is underdamped. So we know what zeta is. We know zeta is equal to 0.5. So we get 4 is equal to 2 zeta omega n. And we also know that 3 plus k is equal to omega n squared. Because right now we need to figure out the value of k corresponding to this point. And from here, we can find that omega n is equal to 4, given that zeta is equal to 0.5. And then from there, we're actually able to determine the gain k as well. So 16 minus 3, so k is equal to 13. So the alternative method. Otherwise, I would have to apply the magnitude criterion, where k is equal to 1 over magnitude of g of s evaluated at s is equal to -2 plus 3.46j. And we would get 13 as well. Both ways will get you the same answer. Two different ways. I'm going to skip the work for finding k is equal to 13. Any questions? So anyway, now what we want to do is we want to do our pole zero placement to reduce our steady state error by 10 times. So the first thing we have to do is find the uncompensated steady state error. So I'm gonna call it ESS for U for uncompensated for step input. So ESSU is going to be equal to 1 over 1 plus, so KPU for the uncompensated system, where KPU is equal to limit as S goes to 0 of K times G of S, where K is equal to 13 from what we found earlier. So we get limit as S goes to 0 of K over S plus 1 times S plus 3, which is equal to 13 over 3. So I plug that in, I get ESSU is equal to 1 over 1 plus 13 over 3, which is equal to 3 over 16. You don't have to keep it in fractions, but I like to because it just makes it easier to see how much I have to reduce a system by. So then we want a 10 times reduction. So we want 10 times reduction, meaning that ESSC is equal to 1 over 10 times ESSU. So that's easy to calculate. So we want ESSC to be equal to 3 over 160. And then that's going to be equal to our the steady state error equation for our compensated system, which is going to be 1 plus KPC. So this is now with our compensated system. And we find that KPC is equal to 157 over 3. So you notice that the gain is much higher. And the definition of KPC is equal to limit as S goes to 0 of C of S multiplied by K times G of S. Which is equal to S plus ZC, limit as S goes to 0 of S plus ZC divided by S plus PC, and we just multiply that by our KP constant. Any questions? So then this is going to be equal to, so KPC is going to be equal to ZC divided by PC multiplied by KPU. And we want that equal to 157 over 3. So we know KPU, we know KPC, we just need to figure out the ratio. And we will continue that tomorrow.